Well, it is 8 a.m. on Monday morning. So today, we'll consider this problem. Let m be a positive integer, and let b be a positive real number such that b is greater than 1. So suppose the functions y equals x to the m and y equals b to the x have the same instantaneous rate of change at a point in the first quadrant where they intersect. Find the point of intersection written as an ordered pair. So just to elaborate a little bit, these two functions intersect at a point, and at that point of intersection, each function has the same instantaneous rate of change as the other function. Well, the instantaneous rate of change of a function is determined by its derivative. So for y equals x to the m, the derivative of y with respect to x is equal to m times x to the m minus 1. And for the exponential function, for y equals b to the x, the derivative of y with respect to x is the natural log of b times b to the x. So in effect, we want to solve a system of equations. Solve this right, solve the system x to the m equals b to the x. That's one equation in the system. And the other equation is where the derivatives are equal. M times x to the m minus 1 equals the other derivative, which is the natural log of b times b to the x. We want to solve this system for x. Well, from the second equation, if we solve this equation for b to the x, we can do so if we divide both sides by the natural log of b. So b to the x is equal to m times x to the m minus 1 divided by the natural log of b. And then in the other equation, we will replace b to the x with this term, m times x to the m minus 1 over the natural log of b. So I'll just write x to the m and then replace b to the x with m times x to the m minus 1 over the natural log of b. And notice if we divide both sides by x to the m minus 1, we find out what x is. X is equal to m divided by the natural log of b. Well, this describes what x is in terms of m and b, m divided by the natural log of b. But we can do better. So in this equation, x to the m equals b to the x. So I'll write that out a little bit. In the equation, x to the m equals b to the x. Replace x with m over the natural log of b. All right, so instead of x to the m, we have m divided by the natural log of b to the m. And we're setting that equal to b to the x, but we're replacing this x with m over the natural log of b also. So we get b to the m over the natural log of b. Then using properties of exponents, we will raise both sides of this equation to the exponent 1 over m. So that's perfectly legal. We raise the left-hand side to the exponent 1 over m. And that requires us to raise the right-hand side to the exponent 1 over m. And then applying the property of exponents, we multiply the exponent 1 over m times m, which is 1. And on the right-hand side, we also multiply the exponents 1 over m times m over the natural log of b. That will just simplify it to b to the 1 over the natural log of b. So this equation becomes m over the natural log of b equal to b to the 1 over the natural log of b. In a couple of minutes, I'll show you how to simplify b to the 1 over the natural log of b to the number e. So this, for as long as b is greater than 1 and not equal to 0, b raised to the exponent 1 over the natural log of b simplifies to the number e, which is approximately 2.71828. And then if we solve this for m, we get m equals e times the natural log of b. Okay, so once again, we're going to use the fact that x equals m over the natural log of b. And in this equation, we're going to replace m with e times the natural log of b. So we get x equals e times the natural log of b divided by the natural log of b. But this just simplifies to the number e. So what we have found is that the x-coordinate of that point of intersection, where the instantaneous rates of change are equal, is the number e. And the y-coordinate, well, since y equals b to the x, we can write y equals b to the e, replacing x with e. Okay, so as an ordered pair, the point of intersection is the ordered pair e, b to the e. The x-coordinate is e, the y-coordinate is b raised to the exponent e. Okay, in this little space here, I'll show you that b to the 1 over the natural log of b can be simplified to e. So I'll start by writing b to the 1 over the natural log of b. Since b is positive, it's also not equal to 1, but all we need is the fact that b is positive we can replace b with e to the natural log of b. And then we're still raising that to the exponent 1 over the natural log of b. And then applying one of the properties of exponents, we can multiply these two exponents. And we get e to the natural log of b over the natural log of b, or e to the first, or e. Okay, so that shows us that b to the 1 over the natural log of b is just the number e. Okay, the next part, we'll consider a more general situation. Solve the equation x to the m equals b to the x. Solve this for x, given that m is a positive integer and b is a real number such that b is greater than 0 and b is not equal to 1. So in this case, we're not requiring that the two functions have the same instantaneous rate of change of intersection. Okay, but I'm just going to suggest something that might seem really weird. I'm going to pick x to be the mth root of b raised to the exponent, which is the mth root of b raised to the exponent of the mth root, and so on. So by the 3 dots, I mean to indicate that what is taking place here goes on forever. So I start out with the mth root of b raised to the exponent, the mth root of b, which is also raised to the exponent of the mth root of b, which is raised to the exponent of the mth root of b, and so on forever. You'll recall that if you take the mth root of something, that's the same as the something raised to the exponent 1 over m. So I'm going to take the outer mth root. So on the inside of the brackets, we'll have b raised to the mth root of b raised to the mth root, and so on forever, but with the outer exponent 1 over m. Okay, then if I raise both sides of this equation to the exponent m, I get x to the m on the left-hand side, and when I raise the right-hand side to the exponent m, I get b to the exponent, which is the mth root of b raised to the mth root of b raised to the exponent, the mth root of b, and so on forever. But notice that the exponent is just what x is. So x to the m is equal to b to the x, where x is this weird-looking expression. An infinite, I don't know how you would, I don't know what a name for this is. Okay, well, there's more than one solution to this generally. You know, in the previous example, we had a special case where there's just one solution in the first quadrant. But if you have more than one solution, then there's another solution besides x as described here. But this is all we're going to do for today. So see you next time.